Hello everyone. Welcome back to another lecture of CSE 230 Discrete Mathematics. I am Sabrina Zamanishita and I'm going to deliver this lecture content to you. Some of you might have guessed what's going to be the lecture topic of today, and you have guessed it right, that is recurrence. So let's get started. We all know that if a function, for example f of n, this function is calling itself with another parameter, for example, n minus 1 with some variation, then this type of relation is regarded as recursion. Now, if we want to express this relation or express this procedure with the help of mathematical expression or mathematical terms, for example, if f of n is expressed by f of n minus 1 with some variation that it would be multiplied by 2, then these type of relations are regarded as recurrences. For example, I'm going to write a sequence for you. This is A0, A1, A2, A3, A4, and so on. In this sequence, there are some terms starting from A0. This is the first term, this is the second one, this is the third one, and so on. Now, if I want to establish a relationship between these terms, that is, if I say that there is a term an and an can be defined by 2 multiplied by an minus 1. That is, a term would be expressed by 2 multiplied by the previous term. For example, a3 would be 2 into a2. So if I write this down serially, that is A1 would be 2A0, A2 would be 2A1, A3 would be 2A2, and so on. So this is a recurrence relationship. But one very important thing is missing here. If we do not know what is the value of A0, then this recurrence relation is invalid. So we need to know what is the value of A0 because without this value, we cannot define this sequence, no matter what relation we have established. So we need this value, and this value is regarded as boundary condition. This is also regarded as base condition. All right, so we need this value. So to express this relation with recurrence, we need to write an would be 2 into an minus 1 and the value of a0 would be something. So this would be a recurrence relation of this sequence. Now if I define a0 is 1, then what would be the form of this recurrence relation? The form of this recurrence relation would be a0 is 1 and we know that a1 is 2 into a0 and that would be 2 into 1, that is 2. So the second term would be 2. Similar way, the third term would be 2 into 2, 2 into 2, that is 4. So a2 would be 4. Same way, a3 would be 8, a4 would be 16, and so on. So for this sequence, we can define it with the help of our recurrence relation. So this was our sequence, and for this sequence, this was the recurrence relation. Now I tell you that you need to calculate A37. So to calculate A37, what you need to do, we know that for any term from this sequence, it can be calculated by this formula. So A37 would be simply 2 into A36. So that would be 2 into A36 is 2 into A35 and A35 is 2 into A34. So how long am I going to go on like this? To A0 because we only know the value of A0 and that is 1. So this type of calculation is really time consuming. So if you want to calculate the value of a term, for example, an, then it would be very nice if we can come up with a simpler solution that requires no calculation like this. So if you look at this sequence closely, then you can find that in this sequence, this is the sequence, I'm going to write it down again. So if we say that this is A0 and this one is A1, this is A2, A3, and A4. So for the value of n is 0, this is 1, this is 2, this is 3, and this is 4. So for the value of n, the term an would be simply 2 to the power n, isn't it? Think about it. If n is 0, then it would be n is 0, then a0 is 2 to the power 0, which is simply 1. And we know the value of a0 is 1. If n is 1, then a1 would be 2 to the power 1, which is simply 2. And we know that a1 is 2. And for n equal to 2, a2 would be 2 to the power 2, which is 4. And we know that at a2 is 4. For n equal to 3, a3 is 2 to the power 8, which is 8. And we know that a3 is 8. So for all other terms, this would be same. So we can say that any nth term of this sequence would be simply 2 to the power n. So we have found our solution. So what we have got, I am going to simplify it. So this is the sequence which was given, and this is our boundary condition, or you can say this is the initial condition or base condition, and this is the recursive relation or recurrence relation. And we have just found out our solution to the recurrence. I'm not doing it, by the way. I don't know why it's happening. Anyway, this recurrence relation that we have just solved by just looking at this sequence is regarded as linear homogeneous recurrence relation. All right, we are mainly focusing on linear recurrence relation, and for this we are going to cover two types that are, so we are going to cover two types of linear recurrence relation. One is homogeneous, another one is non-homogeneous. Let's see what a linear homogeneous recurrence relation is. So a linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relation of this form. So look at this form. What it said is that in a sequence, nth term of this sequence, which is regarded as an, would be written in this form, where C1, C2, Ck, all these are real numbers and these are constants. And an is expressed in terms of previous k terms, as we can see that an is expressed with its previous term, which is an minus 1, and the previous term of that term an minus 2, and so on, and it would go on like this to n minus kth term. So this type of equation is regarded as a linear homogeneous recurrence relation of degree k because an is expressed with the help of previous k terms of the sequence. Now, the example that I have shown you where an is expressed with the help of its previous one term. So in this case, this is regarded as a linear homogeneous recurrence relation, which is of order what? This an depends on its previous term which is a n minus 1. So it depends on previous 1 terms. So this is order k and here k is equal to 1. So this is of order 1. Right? Now look at this one. If an is expressed as a n minus 1 plus twice of a n minus 2. So here we can see that these are constants because 2 is a constant and here C1 would be 1. So this is also a constant. So this would be a linear homogeneous recurrence relation as well of degree what? As we can see, an depends on its previous two consecutive terms. So this would be of degree 2. Now let's say another example. We can express this an as t of n as well, which is the nth term of the sequence. So if it is expressed as t of n equal to 2t n minus 1, that is twice of its previous term, plus 1. So we can see that here t of n is expressed as twice of its previous term plus 1. So for this term here we can see that this term is not in terms of any term of the sequence. So this type of sequence are not regarded as homogeneous sequence. This type of sequences are regarded as non-homogeneous sequences, which will be covered later. First, we will see some examples on homogeneous linear recurrence relations. Now, let's see another example. Here, an or the n term of the sequence is expressed as a n minus 5. So, an is equal to the previous fifth term of the sequence. So, this is a homogeneous sequence, linear homogeneous sequence. We all know that, but what should be the degree of this recurrence relation? You may guess that the degree should be 1 because it depends on one term, but it is not depending on the previous one term. It is depending on the previous fifth term. That's why this would be of degree 5. As we can see here, it was depending on the previous term and only the previous term. That's why its order was 1. And this is depending on its fifth previous term. That's why its order would be 5 or degree would be 5. Now let me give you one last example, that is nth term of the sequence would be expressed as its previous term plus the square of its second previous terms. Now as we can see, there is a square in one of the terms which is used to express the nth term. So these type of recurrence relations are not even linear. That's it. I think after showing these examples, I was able to make your concept of recurrence relations a bit clearer. So let's have a look at the recurrence relation that I have shown you earlier one more time. Now, this was the previous example that I have shown you. And here we can see that this is the sequence and this was the recurrence relation and this was the solution of this recurrence relation. By looking at the sequence, we were able to come up with the solution. Now I'm going to show you another sequence. Before writing it down, I'm going to give you the recurrence relation, which is the nth term of this recurrence relation is expressed as the previous term of the nth term plus 6 times the second previous term of this nth term. So for this recurrence relation, we need to provide the first two terms of this sequence as the boundary condition. So A0 would be 3 here and A1 would be 6 here. So what should be the sequence? The sequence will start with 3, after that 6, then A2, this is A0, this is A1, then A2 would be 6 plus 3 into 6, which is 24. And A3 would be 24 plus 6 into 6, which is 60. This sequence will go on like this. Now, by looking at this sequence and by looking at this recurrence relation, can you come up with the solution of this recurrence relation? Can you? So what should be the solution of this recurrence relation? We cannot simply say what should be the solution of this recurrence relation by simply looking at this sequence. So for this, we need to solve the linear homogeneous recurrence relation. Now, how to solve a linear homogeneous recurrence relation? So the recurrence relation is expressed as the nth term of the sequence would be expressed as this. As we all of know, this is a linear homogeneous recurrence relation. So what we are going to do, we are going to find a solution of the form r to the power n. That is, an can be regarded as f of n as well. Then this would be written as r to the power n. So this would be r to the power n. This one would be c1 r to the power n minus 1, then c2 r to the power n minus 2, and this will go on to ck r to the power n minus k. This relation is a linear homogeneous recurrence relation of order k. So this will go on till ck. Now put all of this in left hand side and right hand side would be 0. After that, what we are going to do, we are going to divide the left hand side with r to the power n minus k. So what is happening here? If we divide r to the power n by r to the power n minus k, then c1 r to the power n minus 1 divided by r to the power n minus k, and lastly ck r to the power n minus k divided by r to the power n minus k, then this will result in r to the power k, obviously, then c1 r to the power, this would be k minus 1, right? I'm just going to show you for your convenience. R to the power n into r to the power minus 1, this is, and then r to the power n into r to the power minus k. So this will be cut out and it would be simply r to the power k minus 1. Okay. So this would be r to the power k minus 1, and it will continue like this till it would be ck only, because these are resulting in 1. So this equation that we have got is called the characteristic equation. All right. So this is the characteristic equation which we have got from this recurrence relation. We're going to assume that R1, R2 till Rm are m number of roots of this characteristic equation, and alpha 1, alpha 2 to alpha m would be any constants. So an would be written in this form. You can pause the video and look at this equation and write it down on your notepad. But if you don't understand what I have been telling you, you will understand it when I will be showing you an example workout. So I'm going to consider a recurrence relation, which is a linear homogeneous recurrence relation, and I'm going to solve it by following these approaches, and I'm going to come up with the solution of that recurrence relation. Let's look at an example workout. So let's have an example on which we are going to apply the approaches to find the solution of this recurrence relation. So this is the example that I'm considering, where the nth term of the sequence would be calculated by the previous term plus 6 times the second previous terms. And the boundary conditions are a0 would be 3 and a1 would be 6. If you can remember, this is the very same example that I have shown you, but we couldn't figure out the solution of this recurrence relation by just looking at this sequence and this recurrence relation. So I'm going to follow the approaches to find the solution. So what we're going to do, we're going to put all the part of this right hand side to left hand side and make the right hand side 0. So let's do that. And I'm going to replace an by r to the power n. So it would be r to the power n minus r to the power n minus 1 minus 6 r to the power n minus 2. Now what I'm going to do, I'm going to divide this by r to the power n minus 2. That is the smallest term, and that's how you have to do it for all the sequences. So it would be r square minus r square minus r minus 6 equal to 0. So let's solve this equation. So there should be two roots of this equation. You know how to do that? So the two roots that we got are r1 would be 3 and r2 would be minus 2. Two values of r, I'm just naming them as r1 and r2. Alright, now what should be our solution? Our solution should be a n equal to alpha 1 r1 to the power n plus alpha 2 r2 to the power n. We know the values of r1 and r2, but we don't know the values of alpha 1 and alpha 2. So what we're going to do, we're going to find out the values of alpha 1 and alpha 2. So from here, a0, that is the value of n is 0. So a0 is 3. So if we put n equal to 0, then this would be alpha 1 r1, the value of r1 is 3 to the power 0 plus alpha 2, the value of r2, which is minus 2 to the power 0. And this will result in alpha 1 plus alpha 2. So this is equal to 3. After that, a1 equal to 6. So alpha 1, 3 to the power 1 plus alpha 2 minus 2 to the power 1. So this will be 3 alpha 1 minus 2 alpha 2 equal to 6. Now if this is equation 1 and this is equation 2, from 1 and 2, if we multiply the equation 1 by 2 and then add it with equation 2, then it will result in 2 alpha 1 plus 3 alpha 1, that would be 5 alpha 1. 2 alpha 1 minus 2 alpha 1, that would be 0. And 3 into 2 is 6. 6 plus 6 would be 12. So alpha 1 is 12 by 5. We have got the value of alpha 1. And if we put this value in equation 1, then alpha 2 would be 3 minus 12 by 5, and that is 3 by 5. So we have got the values. Now put these values in this equation, this one. So our solution is an, or the nth term of the sequence, is 12 by 5, 3 to the power n, because the value of r1 is 3, plus 3 by 5, value of alpha 2 is 3 by 5, then minus 2 to the power n, because the value of r2 is minus 2. So this is our solution that we have got. Now let's verify whether this solution is right or wrong. Here the value of a0 is 3, the value of a1 is 6, and we know the value of a2 would be 6 plus 3 into 6, that is 6 plus 18, which is 24. If you can remember, we have shown that before. So a2 is 24. Let's put this in this equation where n equal to 2. If n equal to 2, that would be 12 by 5, 3 to the power 2, or 3 square, plus 3 by 5 minus 2 square. So it would be 12 by 5 into 9 plus 3 by 5 into 4. Minus 2 into minus 2 is 4. So 4 into 3, 12 divided by 5. So if we take 12 by 5 as common, then it would be 9 plus 1. So let me write it here. 12 by 5 into 10. This is 2, and 12 into 2 is 24. So this is the same value as this one. So this equation works. So this is our final solution of this recurrence relation, which is a linear homogeneous recurrence relation. Let's move on to the next lecture and have some more examples. Thank you, everyone.